This video is going to hopefully help you better understand the rational root theorem. I'm going to give you a little background on this that your book kind of glazes over a little bit. I'm going to talk to you about the rational zero theorem, which I have it spelled out here. I've got this from the Algebra 2 book. So what the rational zero theorem tells you is if you have a polynomial, integer coefficients, then every rational zero of your function is in the form of p over q, where p is the factor of the constant divided by the factor of the lead coefficient. Okay, so what this can help you do is it can help you get a list of all the possible rational zeros or rational roots of a function. So let me explain this a little bit with something that you understand, and hopefully this will make sense to you, with something simple. Here's a function, you can factor it, okay? It's a trinomial, it's factored easily. The zeros of this function are gonna be whatever x would equal to make the entire function zero. Well, if this is zero, the whole function's zero. If this is zero, the whole function's zero. So if x is 4, or if x is negative 1/2, we have zeros. That will make f of x equal to 0. If I plug in 4 in for this is 0. 0 times doesn't matter what this is, I get 0. Okay, so what I want you to do is look at this. So I'm going to rewrite this. This is the same as 4 over 1, right? I'm writing it in the ratio of p over q. P, 4, has to be a factor of the constant a sub 0. Is 4 a factor of 4? Yes. Q has to be a factor of the lead coefficient. Is 1 a factor of the lead coefficient? Yes, it is. 2 and 1 are the factors. For this one, is 1 a factor of the constant? Yes, it is. Is 2 a factor of the lead coefficient? Yes, it is. So your zeros have to be in that form of p over q, where p is the factor of a constant, of the constant term, and q has to be a factor of the lead coefficient. So what this can do, along with the rational root theorem, this is going to be able to help you break down very large polynomials and factor them when you couldn't do it before. Okay? So you're going to keep this in mind, and we're going to use this new rational root theorem, which basically tells you, which hopefully it makes sense, if ax minus b is a factor, it is a factor if and only if p of b over a is 0. So what that's saying is ax minus b. If that's a factor, if I set that to 0, x has to be b over a. Okay? So if I plug in b over a into my function, which is what I did here, if I plug in 4, I get 0. Okay? So if ax minus b is the factor, then b over a is the 0. Okay? So we need to use this information to factor this polynomial. So you're going to try to factor this. And you have no idea where to start. There's no common factors. The first thing you're going to do is list all the possible zeros, all the possible roots, okay? Real root, or the possible rational roots. So I need to know that those are in the form of p over q, where p is a factor of the constant, and q is a factor of the lead coefficient. So I'm going to write down all my possible p's. All my possible p's are going to be plus or minus 2, or plus or minus 1. Those are the only factors of 2. My possible q's are plus or minus 3, or plus or minus 1. So what are all my different combinations of p over q can I have with those numbers? Okay, I can have 2 over 3 plus or minus. I can have 2 over 1 plus or minus. And I can have 1 over 3 plus or minus. And I can have 1 over 1 plus or minus. Okay, so I have 8 different possible roots. Okay, and if I simplify these, they look like plus or minus 2/3, plus or minus 2, plus or minus 1/3, and plus or minus 1. Okay, so I'm going to pick, I have no idea if these are possible roots. They may not actually be a root. Okay, so I'm going to check one, and I'm just going to pick one randomly. This is where this can get really tedious, but in the future, after I give you an example or two and you kind of get the hang of it, I'm going to let you use your calculator to help narrow down some of these zeros, okay? So I'm going to use synthetic division, because if I take this 1, I'm going to try 1, and it could be -1. I mean, like I said, we have 8 different possibilities. And I'm going to use synthetic division to see if I get 0 for my remainder. And if I get 0 for my remainder, that means that if I plug this into my original function, I would get 0, and it would be a 0. So I'm going to go ahead and try to figure that out. So I'm going to use the synthetic division that I showed you today, and this will give you a little more practice with this. So I'm going to just put all the coefficients from my polynomial. I'm going to bring down the 3. That's how you get to start. 1 times 3 is 3. Then I'm going to add 1. 1 times 1 is 1. I'm going to add the column, -6. 1 times -6 is -6. And when I add those together, I get -8. So I have a remainder. So unfortunately, 1 is not a 0 of the polynomial. All right, so I'm going to try another one. Let me see if I can kind of make a line here and kind of separate this. Let me try another one. Let's try 2. Okay, so I'm going to, and the reason I'm doing synthetic division instead of just plugging 1 into the function to see if I get 0, I do have a reason for that, and you're going to see that in a minute. Okay, so let me go ahead and do this again. This is -2, and then -7, and -2. I'm going to bring down the 3 and get started. 2 times 3 is 6. Add the column, I get 4. 2 times 4 is 8. Add the column, I get 1. 2 times 2 is 2. Add the column, I get 0. 2 is a 0 of my polynomial. So remember if I said, so that, what did I just, and the reason I chose to do synthetic division is because basically what I've done is I've divided this polynomial by x minus 2. Remember how I said that if 2 is the 0, then x minus 2 has to be the factor? So what I've just said is, okay, x minus 2 is a factor. I've just figured that out. Now, these coefficients are basically what's left after you divide x minus 2 into this polynomial. So that would be 3x squared minus, plus 4x plus 1, okay? So this times this gives me this. This was basically a quick way to do some long division. Now, x minus 2, now I can factor this. I know how to factor this. This is not that hard to factor. What are the factors of 1, 1, and 1? Okay, so does this work? This is positive, positive, they're both positive. So these are the factors of this polynomial. I just factored that polynomial using that theorem. So if these are my factors, my zeros, okay, or my roots are x equals 2, x equals -1, and x equals -1/3. Now, are those part of my list of possibilities? Yes, they all 3 are. Okay, so that function actually let me factor this polynomial. So it's really, really powerful, and it can be pretty cool. Now, we'll work some more in class, and I know that just randomly picking these numbers could be kind of ridiculous. So I will normally either tell you, give you one to try to get started so that you hit it faster, or another way to do it is if you graph this polynomial and you can tell that it's crossing the x-axis at a nice pretty number like 2, -1. If you can tell that, for example, if you graph this, you would have been able to see it crossing at 2 and -1. This might not have been so clear to you though. Like -1/3, you might not have been able to tell exactly. So you would still have to kind of go through this process to break it down. And sometimes you won't have, all of your roots won't be rational, or all of your roots won't be real. So you'll have to deal with that. So this is a pretty good way to do that. So hopefully that clarifies a little bit what we started in class today.